we had set up the Fourier series earlier in terms of trigonometric functions. Now there is an alternative way of setting up the Fourier series. This will be in terms of exponential functions. Let us proceed to do that. In terms of exponential functions. You recall that f of t we had written in terms of trigonometric functions as a naught plus the sum of cosine terms plus bn sin n omega naught t sum of sine terms. Now we can express sine and cosine terms in terms of exponential functions. So I can write this as an e to the power of jn omega naught t plus e to the power of minus jn omega naught t divided by 2 plus bn e to the power of jn omega naught t minus e to the power of minus jn omega naught t divided by 2j. N from 1 to infinity. Now we have e to the power of jn omega naught t terms here as well as here. So let us group them together so that we write this series in terms of exponential functions. So you have a naught plus what is the coefficient of e to the power of jn omega naught t? an upon 2 plus bn upon 2j. So I can write this as an minus jbn upon 2. This is the coefficient of e to the power of jn omega naught t. N ranging from 1 to infinity. We also have terms like e to the power of minus jn omega naught t. And what is its coefficient? An upon 2. And then because the negative sign here, it is plus jbn upon 2. N from 1 to infinity. So what we have done is we express f of t not in terms of trigonometric functions but in terms of exponential functions of the type a j e to the power of jn omega naught t. Now we would like to, in the context of expansion in terms of Fourier exponential functions, we would like to indicate the coefficients in a different way. So we will call this Cn, a complex number Cn, and this will be Cn conjugate. And since we are calling the exponential in the coefficients, given the symbol C for the various coefficients, we may as well call this C naught. Therefore I can write this as C naught plus n from 1 to infinity. Just to indicate that this is a complex number Cn, I will put a line on top, that is a complex coefficient, e to the power of jn omega naught t plus n from 1 to infinity, this is Cn conjugate. because this is an minus jbn upon 2 is cn, this is its conjugate, the angle, the imaginary part has its sign reversed, e to the power of minus jn omega naught t. So let us define Cn star as C minus n. Then we have f of t as C naught plus Cn e to the power of jn omega naught t, n ranging from 1 to infinity, C minus n e to the power of minus jn omega naught t. Now we would like to combine these two summations into one. That can easily be done by substituting minus n for n here, in which case when you substitute minus n for n here, then I can write this as C naught n from 1 to infinity Cn e to the power of jn omega naught t. So when you change the dummy sign of summation minus n by n, therefore this n goes from minus 1 to minus infinity. This is Cn e to the power of jn omega naught t. Combining these two, I can write n from minus infinity to plus infinity, including this 0, minus 1 to infinity, minus infinity to minus 1, 0 and 1 to infinity, Cn e to the power of jn omega naught t. This is f of t, where we observe that C minus n is Cn conjugate, which is An plus jbn upon 2, because Cn conjugate is An plus jbn upon 2. So this is a very compact way of representing the Fourier series. You don't have two groups of terms like A coefficients and B coefficients. You have only to deal with a single set of coefficients Cn. The question is, how is the Cn related to An and Bn? That we already have seen, that Cn equals An minus jbn upon 2. And in anticipation of this, suppose I take the magnitude of Cn, it is Cn square root of An squared plus Bn squared upon 2, or in other words, square root of An squared plus Bn squared equals 2Cn. So in anticipation of this notation only, when we put the Fourier series expansion of a function in trigonometric form, trigonometric functions, we said the amplitude of the nth harmonic is 2Cn rather than Cn. It is in anticipation of this formula. Now the next question that we would like to ask is, how do we evaluate the Cn coefficients? What is the formula for that? In the same way as we have done for the trigonometric functions, how do we get this complex coefficient Cn directly from the f of t? This can be easily derived as follows. Cn we know is An minus jbn upon 2. And we know the formulas for An and Bn. Let us substitute that. This is half of An is 2 upon t naught f of t cos n omega naught t dt over a period. And for Bn, I can write 2 upon t naught f of t sin n omega naught t dt. This j term comes from here. This half, of course, is substituted here. Now these two integrals can be combined. First of all, I can take a 2 by t term, t naught term outside. So 1 upon t naught, 0 to t naught, f of t cos n omega naught t minus j sin n omega naught t and this we know is e to the power of j n omega naught t. So the integral that needs to be carried out to evaluate Cn is like this. This is really the average of f of t multiplied by e to the power of minus j n omega naught t. What do we observe here? And what are the merits of this exponential function, the exponential form of the Fourier series? First of all, we observe that we have only one single formula for evaluating the various Fourier coefficients. You don't have separate formulas for a0, an, and bn. And the notation is very compact. More importantly, when we extend this concept of Fourier expansion of periodic functions to aperiodic functions, what we will refer to as Fourier integral concept, which we will take up later. There, these expressions for Cn can be, in a more straightforward fashion, extended to the Fourier integral concept than if we had persisted with an and bn. So we have a single formula valid for all n. The notation is compact, and the notation can be extended to the Fourier integral quite conveniently. That is the important thing. So in the Fourier expansion for this, we note that each term by itself may not convey to us any physical signal, because when you substitute a value, real value of time, this does not, by each term by itself will not yield a real value of the function. However, we have to bear in mind that if you take Cn e to the power of j n omega naught t and combine this with C minus n e to the power of minus j n omega naught t, these two together will lead to a real function of time, a sinusoid, which will be 2Cn cos n omega naught t. This one. You can easily show that. So the amplitude of the nth harmonic component is 2Cn, and this real function of time comes by combining the two exponential terms for plus n and minus n respectively. So individually there is not a physical signal, but when you combine these two, this is the conjugate of this, you will get this. Right. Now let us work out an example illustrating the exponential form of Fourier series. We take the same example that we have worked out earlier, a square wave, because we can compare the results. So this is f of t. We would like to find out the Fourier series expansion in exponential form. So Cn would be, easy way to remember would be average of f of t multiplied by e to the power of minus jn omega naught t. This is what we have to find out. So that will be 1 over t naught, and to find out the integral of project, we split this up into integral in two parts, one from 0 to t naught upon 2 and the other t naught upon 2 t naught, because the value of the function changes in these two intervals. Therefore, I can write this as
10 minutes left.
1 over t naught (0 to t naught upon 2), the value of the function is a e to the power of minus jn omega naught t dt plus t naught upon 2 to t naught, and in this interval the value of the function is minus a minus jn omega naught t dt. So I take the a outside, a upon t naught, the first integral will yield e to the power of minus jn omega naught t by minus jn omega naught, minus, because of this minus sign here, e to the power of minus jn omega naught t divided by minus jn omega naught, and the first integral is evaluated between 0 and t naught upon 2. The second integral is evaluated between t naught upon 2 and the t naught. So you can take out minus jn omega naught outside, and if you evaluate this, it will be e to the power of minus jn at the upper limit. Omega naught t naught upon 2 is pi minus jn pi. At the lower limit, it is 1 minus 1, and minus at the upper limit, it is minus jn omega naught t naught is 2 pi. Therefore, e to the power of jn 2 pi, it's equivalent to 1 because it's an integral multiple of pi. Therefore, 2 pi is minus 1, and the lower limit, because the minus sign, it becomes plus e to the power of minus jn pi, because t naught upon 2 multiplied by omega naught equals pi, leads to pi. Therefore, this can be written as minus jn omega naught t naught. These two can be combined into 2 times e to the power of minus jn pi and minus 2. Therefore, 2a times e to the power of minus jn pi minus 1. And e to the power of minus jn pi is either plus 1 or minus 1 depending upon the value of n. Therefore, if n is even, this becomes 1. Therefore, this leads to 0, 1 minus 1. If n is odd, then e to the power of the angle is an odd multiple of pi. Therefore, this minus 1. So you have a minus 2, minus 1, minus 2. Therefore, it will become, this j can be taken out. Therefore, this will become minus 4a divided by n omega naught t naught and a j in front, and omega naught t naught is 2 pi. Therefore, this will be minus j 2a by n pi. For n naught. And since we know that Cn equals An minus jBn by 2. Therefore, what we now see is Bn upon 2 is 2a by n pi. From this we conclude that Bn equals 4a by n pi, a result which we already have obtained from the trigonometric form of Fourier. So this ties up with that. C naught of course is 0 because the average value of this is 0. And it's when we are carrying out this analysis to find out the Cn, it would always be advisable for us to arrive at the C naught value independently rather than the straight formula of substituting n, because sometimes when n equal to 0, it leads to some difficulties, some degeneracies, because n may come in the denominator. So it's always advisable to calculate C naught independently rather than substituting n equals 0 in the general formula. Sometimes it may work, sometimes it may not. Now we have discussed symmetry conditions in relation to the A and B coefficients. Now what are the similar conditions that are applicable to the Cn coefficients? So let us now discuss that. If f of t is even, we said that only the cosine terms are present, that is an terms are present, not the bn terms. Since we know that Cn is an minus jbn by 2, if f of t is even, it means that Cn is real, because Cn is an minus jbn upon 2. So if bn is absent, then Cn is purely real. The angle associated with the complex number is 0. If f of t is odd, then of course Cn is purely imaginary. You have the bn terms but no an terms. And if f of t exhibits half-wave symmetry, then as before we have only the odd harmonics present. Cn can exist only for odd n. Even harmonics are absent. So to summarize what we have done in this lecture, we started with an example in which we have taken a half-wave rectified sine wave, found out its Fourier series, making effective use of the symmetry conditions. We saw that a half-wave sinusoid can be expressed, broken up into its even part and odd part. The odd part was a pure sine wave. The even part was a full wave rectified sine wave, where whatever waveform is there in one half cycle is reproduced, and therefore we have only the even harmonics present, and we have found out the Fourier series expansion of the even part and odd part separately, and use such a kind of waveform in a practical circuit consisting of an R and C, a rectifier circuit, and use that example to illustrate how we can make use of Fourier series in analyzing the steady state performance of a simple RC circuit. Then we took up the question of Fourier series expansion in terms of exponential functions. So in terms of exponential functions, we expressed f of t as a summation of various terms, each term being of the form Cn e to the power of jn omega t, jn omega naught t, where Cn is a complex coefficient in general which is related to the A and B coefficient that we already talked about as Cn equals An minus jBn upon 2. And we found out that the expression for calculating C of n is quite surprisingly simple. It is simply the average of f of t times e to the power of minus jn omega naught t, valid for all values of n. And we said that expansion in this form is useful for us when we later go to the Fourier integral form, apart from its compactness and the fact that we have to calculate only one set of coefficients, that is Cn coefficients, instead of having to calculate An and Jbn separately. The price we have to pay for that is, of course, we have to use complex algebra because Cn is a complex number, whereas if we are calculating An and Bn, we have to deal with real functions only. So we have to pay a price for it, but nevertheless it leads to a very compact notation. So we have two alternative ways of expressing Fourier series, one in terms of the An and Bn coefficients, other in terms of Cn, and one can always convert one set of coefficients into the other. We took up a square wave as an illustration and showed that expansion in terms of Cn will, of course, naturally, as we expect, leads to the same results, but of course Cn now is an imaginary quantity. That means this is related to Bn, which is 4a by n pi, which we already found out. And lastly, we talked about symmetry conditions in terms of the Fourier coefficients of the trigonometric expansion or the exponential expansion, and we said if f of t is even, Cn happens to be real. If f of t is odd, Cn is purely imaginary. And the half wave symmetry, which we already discussed with, doesn't yield any new surprising results. Of course, we know that once the f of t equals minus of f of t plus t naught upon 2, which means that the wave is reproduced with a negative sign in the succeeding half cycle, then the only even harmonics are present, and therefore Cn can exist only for odd n. Some of these, for some odd values of n, Cn may not exist also, but if at all it can exist, it can exist only for odd values of n.